Good morning, everyone. My name is Jian Liu. I'm from Stevens Institute of Technology. Today, I'm going to present our work, Snooping Keystrokes with millimeter-level audio ranging on a single phone. So this is a joint work with Rutgers University and Florida State University. Mobile device hardware is increasingly supporting high-definition audio capabilities for the better user experience. It includes multiple microphones for the stereo recording and noise cancelling, as well as a greater improvement in the audio sampling rates. For example, Samsung Galaxy Note 3 has equipped with 3 microphones, which are used for the stereo recording and noise cancelling. And its audio chipset is capable of 192 kHz playback and recording. So given this advancement, such advancement could definitely improve users' experience, but it also has significant impact on the accuracy of the audio ranging, even bring many security concerns. So such audio advancement could enable many localization-based applications, such as tracking multiple speakers in a meeting room or sensing touch interaction on a surface. It may also have security implications to facilitate the keystroke snooping. So we use this case to understand the limits of this localization approach. We know that it's very common for users to play their phones on the desk while working on keyboard. Moreover, the tablets or large phones are frequently used with external Bluetooth keyboards where the phone is placed directly behind the keyboard. Therefore, an adversary could simply install a malware into the target user's phone with microphone access to eavesdrop keystrokes. In addition, there are also many opportunities for an adversary to leave a phone nearby the target user's phone, target user's keyboard to eavesdrop keystrokes, perhaps in a confined setting such as laboratories where the physical proximity is not suspicious. Now, given this background, we can ask a question. Can a nearby phone really hear what we are typing? Existing research has already recognized the significance of this question. Actually, most of the existing solutions are context-based, such as adding English language model or dictionary to guess the potential words or sentences the user typed. However, such methods improve keystroke recognition only for natural English language and fail for other languages or strong password composed of random characters. Of course, there also exist several context-free work. However, some of them require extensive label training data for exact keyboard setting to learn acoustic profile for each key. For example, they always require a user repeatedly type a key to generate a label training data, which can be very challenging to obtain for an adversary. Another one doesn't require any training, but it requires the cooperation of multiple nearby phones, making their approach less feasible in real attack scenario. So the use of multiple recording devices, the need for linguistic model, or training with label data, none of these techniques can be easily used in practice to snoop keystrokes, especially for the attack scenario. So here is our work. Different from existing solutions with advanced audio capabilities, we seek to achieve 3 goals. It doesn't require any linguistic model, allowing it to recover the typing in any languages, even random keystrokes. We don't need any priori label training data, which can be very challenging to obtain for an adversary. And the most important is that our approach is only based on one single phone. So let's first look at what we can achieve using advanced audio components in a single phone. Here is the Samsung Galaxy Note 3. 2 microphones are equipped on the top and the bottom edge for the stereo recording. And the third one is on the bottom right side for the noise cancelling. But Android doesn't provide any API to record 3-channel audio with 3 microphones. So the best way we can achieve so far is to utilize these 2 microphones for the stereo recording in our work. So in our work, we mainly use this top side and the bottom side microphones, these 2 distributed microphones. In addition, these smartphones also support high sampling rates. For example, given the highest sampling rate, 192 kHz of audio chipset, Android 4 and Android 5 could support up to 48 kHz and 96 kHz respectively. So now we have 2 microphones. What can we obtain from these two microphones to snoop keystrokes? We found that there are two useful features can be derived from the dual microphone in your phone to snoop keystrokes. The first one is time difference of arrival. Actually, for certain placements of the phone relative to the keyboard, there exist measurable differences in time difference of arrival between most keys. If we know the relative position of the phone to the keyboard, we can obtain the distance difference from each key to the dual microphones and calculate the expected TDOA by dividing the sound speed. We also call this value as a theoretical TDOA. Meanwhile, when a finger clicks a key, the keystroke sound propagates from the key, and the dual microphone of a nearby phone can detect the time difference of the keystroke sound arrival, which is measured TDOA. So this measured TDOA is measured by these two microphones. In this way, we can differentiate those keys by measuring different TDOA. However, using TDOA from two microphones may not uniquely identify each keystroke. This is because based on one single TDOA value, the location of the sound source may be at any position of a half hyperbola, as illustrated by this red curve. And this half hyperbola typically crosses a group of keys of a nearby keyboard. So the sound source may be any one of these darker keys. In addition, the keystroke sound recorded by a nearby phone is digitized by an ADC before it becomes accessible to the applications. Therefore, the measured TDOA can be only presented as the number of delayed digital samples, whose resolution is limited by the sampling rate of the smartphone. For example, given 48 kHz sampling rates could result in 0.02 milliseconds TDOA resolution, while 192 kHz sampling rate has even higher resolution, that is 0.005 milliseconds. So due to all of these limitations, we need other features to help TDOA discriminate close-by keys. We therefore utilize the fine-grained acoustic signature inherent from keystroke sound to help distinguish the keystrokes from different keys, but with similar TDOA. The intuition behind this is because the keystroke sound from different keys are different. I believe for most keyboards, everyone can distinguish whether a keystroke sound is from an alphabet key or from a space key, because they sound very different. Actually, for the alphabet keys, they also sound different, although we couldn't use our ears to distinguish them. But such difference can be well captured by the analysis in the frequency domain of the keystroke sound. For example, using Captron feature, MFCC could even distinguish this difference that can hardly be told by our ears. Now we have two kinds of features, TDOA, and the other is acoustic signature. So how to combine them together to achieve our goals to identify each keystroke? Let's take a look at our system overview. In our system first takes as input a set of keystroke sound recorded by a nearby phone. It then detects and segments the acoustic signal corresponding to the keystrokes and derives the measured TDOA for each keystroke. Meanwhile, given the known relative position of the phone to the keyboard, we can compute a theoretical TDOA for each key. So based on this information, we then divide the keys of the keyboard into multiple theoretical key groups, which are groups of keys whose theoretical TDOAs are too similar to be distinguished. Next is performs grouping of keystrokes to categorize each input keystroke into the derived theoretical key groups. Our system then extracts the acoustic signature from the keystroke sound to further cluster keystrokes within each group, so that after clustering, each cluster only contains the keystrokes of the same key. Finally, our system performs the key labeling with letters to recover keystrokes by examining the distance difference of the mean TDOA of each cluster to that of the theoretical TDOA. So the main task in our work is to categorize input keystroke into the derived theoretical key groups, then use fine-grained acoustic signature to do the further clustering to discriminate the keystrokes of the different keys. In our work, we derive a set of keystrokes based on theoretical TDOAs with no relative position of the phone to the keyboard. In particular, we first saw the keys based on their corresponding spherical TDOAs. In this figure, each right point represents a key, and x-axis is a key ID, y-axis is corresponding spherical TDOA. We first do the sorting. We then link any pair of keys whose difference in spherical TDOAs is less than a threshold. Finally, each connected set of keys is considered as one theoretical key group. We found that by using a threshold of 1/48 milliseconds, in our primary scenario where the phone is placed directly behind the keyboard, 26 alphabet keys can be grouped into 13 theoretical key groups. So after derived theoretical key groups, we need to categorize each input keystroke into these derived theoretical key groups. In particular, we first segment keystroke sound by examining the energy level of the acoustic signal. We then derive the measured TDOA between the acoustic signal from two microphones by using the cross correlation. The measured TDOA is compared to the theoretical TDOAs in every theoretical key groups, and the input keystroke will be assigned to the theoretical key groups whose keys theoretical TDOAs have minimum distance to the measured TDOA of that input keystroke. As I said before, different keys sound different. We further cluster keystrokes within each group based on MFCC features. To illustrate the effectiveness of using MFCC features to discriminate keystrokes of different keys within each group, we observe that the MFCC features of the same key present higher correlation than that of the different keys. It thus appears promising to use MFCC features to discriminate the keystrokes of the different keys in each group. Although the keystrokes in the same theoretical key group have similar TDOA, we observe that the caption features, such as MFCC, of different keys are different. We thus use caption feature MFCC to capture this difference and perform k-means-based clustering in each group, so that after clustering, each cluster only contains the keystrokes of the same key. Now we have multiple clusters, and each cluster only contains the keystrokes of the same key. So we need to label each cluster to recover the input keystrokes. To further label each cluster, we compare the mean TDOA of each cluster to the theoretical TDOAs. And the keystroke in each cluster will be labeled as a key whose theoretical TDOA has a minimum distance to the mean TDOA of that cluster. The intuition behind this is because the mean TDOA of a set of keystrokes emitted from a same key is very close to its corresponding theoretical TDOA. Now you may ask, how robust is the system recurring keystrokes from the different keyboards? What's the performance with different sampling rates of the smartphone? And how does the placement of the phone influence the snooping accuracy? We will focus to answer the first two questions of our experimental results. For the last one, placement accuracy, you can refer the details in our paper. So in our experiments, we used the Samsung Galaxy Note 3 as mobile phone to launch attacks, whose sampling rate is 48 kilohertz. We also emulate the higher sampling rates, such as 96 kilohertz or 192 kilohertz, by using a pair of external microphones, where the distance of these two external microphones is exactly the same as that of the Note 3. So we use this setup to simulate the Samsung Galaxy Note 3 with 96 and 192 kilohertz sampling rates. We evaluate our system with different keyboards that produce different keystroke sound intensity levels. And they are Apple wireless keyboard, Microsoft Surface keyboard, and a mechanical keyboard, Razer Black Widow Ultimate. Typically, the keystroke sound from the mechanical keyboard is much louder than that from the Apple wireless keyboard, and the keystroke sound from the Microsoft Surface keyboard is the weakest. We focused on experiment on the 26 alphabet keys on the keyboard, but our approach can also apply to the whole keyboard. In the data collection, we randomly type the 26 alphabet keys A to Z on the keyboard in typical office environments with ambient noises. In total, there are over 3,000 keystrokes being collected in our evaluation part. For the placement, we focus on our primary attack scenario where the phone is placed directly behind the keyboard, but we also tried other two typical placements where the phone is placed in front of the keyboard and on the left side of the keyboard. To evaluate our system, we use the top K accuracy as evaluation metric. Actually, for each input keystroke, we try to identify K candidates keys for each keystroke. So the top K accuracy is a percentage of the keystrokes that are correctly identified as one of these K candidates among all keystrokes. We evaluate our performance with 3 different kinds of keyboards. So in this figure, x-axis is the different kinds of keyboards, y-axis is top K accuracy, while the different column bar represents the different value of K. In particular, we can achieve the average top 1 accuracy of all 3 keyboards around 86%, while the top 2 accuracy and the top 3 accuracy could be increased to the 95% and 98% respectively. We observed that all 3 keyboards could achieve comparable high accuracies, and such results could demonstrate our training-free, context-free approach could provide sufficient accuracy to snoop keystrokes. We further studied the impact of different sampling rates of the smartphone. In particular, the top 1 accuracy is increased from 85% to 94% when increased the sampling rate from 48 kHz to 192 kHz. We observed that higher sampling rate indeed improves the recognition accuracy because it could provide higher TDOA resolution to help distinguish the close-by keys. Let's conclude our work. We demonstrate a single phone can recover keystroke by utilizing fine-grained acoustic signature and millimeter-level audio region, TDOA. We also develop a training-free approach on a single phone that doesn't require any linguistic model, allowing it to recover the typing in any languages. Also, this makes our approach more suitable for the attack scenario. Our extensive experiments with different keyboards, different sampling rates of the smartphone, different placement of the phone demonstrate that our work could provide sufficient accuracy to snoop keystrokes. So, at last, I would like to say, we hope this fine-grained localization detection approach will not be used by the gas, but could facilitate many other applications to improve the user's experience. Okay, thank you.